All right, I think we can go ahead and get started. Welcome everyone, and thanks for joining us for the final module in our CUDA training series. My name is Tom Papatheodore. I'm with the OLCF. Also on the call, we have Helen He and Kevin Gott from the NERSC LBL side of the organizing. Today, as always, we're joined by Bob Cravella, Robbie Searles, and Max Katz from NVIDIA. They'll be presenting on cooperative groups today. Bob will start off giving a presentation, and then Robbie and Max will follow up with a demonstration as a hands-on component if you wanted to follow along to solidify some of the things you learned in Bob's talk. If you want to ask questions during the talk, please do so in the Zoom chat, and then Bob will handle those either during or after the talk. After the talk, if you want to just unmute yourself and ask questions at that point, or during the hands-on, that's fine as well. So before handing things off today, I would like to just take the opportunity to thank Bob, Robbie, and Max for putting this series together. You know, this is something that the training materials, the slides, the recordings, the exercises will be available for your use after this event is over. And also, you know, it's something that'll be available for future OLCF and NERSC users, as well as just the general public, right, who ends up finding this site. So we really appreciate our friends at NVIDIA putting together such an excellent training series. All right, and with that, I think I can pass things off to Bob and let him get started.
Okay, thanks, Tom. Can you hear me okay?
Yep, I can hear you.
Great. Thanks. This is Bob Cravella with NVIDIA Corporation. I'd like to thank my colleagues, Max and Robbie, for their efforts today and throughout the series. I'd also like to thank the folks at Oak Ridge and the folks at NERSC, especially Tom and Helen, who have provided all the logistics necessary to make this series a reality. So we appreciate that. As Tom mentioned, this is actually the last episode. This is the final module in this CUDA training series. So I also want to thank everyone who has joined me throughout the series and perhaps stuck through or stuck with me all the way to the end here, and I'll just say kudos for that. So this is our last module, and as I've mentioned previously, after around the first 4 or 5 modules in this series, we started to get fairly topical, looking at things that were not necessarily foundational to CUDA programming, but exploring areas that extended the CUDA programming model in one way or another, or extended your skills as a CUDA programmer in one way or another. And that's true of this topic here today as well. Cooperative groups is something that was instituted or added to the CUDA programming model in the CUDA 9 timeframe. We're now in what I would call the CUDA 11 timeframe, so CUDA 9 was several years ago, but nevertheless, this is not something that was part of the CUDA programming model from day one, and it's something that has been added. And the addition, I would say, at least partly is motivated by the idea that we're addressing what we could call or perceive as a gap in the CUDA programming model, something that prevented complete flexibility as a programmer. And hopefully as we get towards the middle of this or towards the end of this module, you'll see what I mean and perhaps agree with me. So we're going to be talking about cooperative groups, and we can break this module up into several pieces. There's going to be an underlying thread or commonality amongst all of these topics here, the thread block level, grid level, multi-device, and coalesced group. There's definitely a lot of commonality. However, they each are a little bit different syntactically, and they each have functional and serve different purposes as well. Just like in the previous modules, we have suggestions for further study, and the homework, and I'll probably try and refer to each of those as I go through the module at certain points. So let's get started with cooperative groups. And I want to start with a little bit of motivation. I'll try to give you motivation at various points along the way during this module. But we're going to start out by declaring that this cooperative groups system or set of functionality is aimed at providing exactly what the name suggests. It's basically cooperation amongst, if you're not intending to speak, could you go on mute? Thank you. This subsystem, this cooperative groups functionality is intended to provide primarily for cooperation amongst groups of threads. And we've actually, in our second module, I believe, in this series, we looked at what is the meaning of thread cooperation, and we studied ideas like sync threads and eventually shared memory. And we talked about those two basic ideas, that cooperation amongst threads in our massively thread parallel programming environment called CUDA largely boils down to two basic ideas, and that is synchronization or execution control, and we can think of things like execution barriers here, as well as inter-thread communication, being able to share data from one thread to another in some fashion. That's basically what, if we decompose, what do we mean by cooperation? Those are the basic ideas, the building blocks that we will use to build lots of cooperative algorithms. We're also going to look at being able to generate flexible parallel decomposition, so being able to take larger groups and subdivide them into smaller groups. And this also ties into the next topic as we think about the idea that we have varying sized groups of threads for purposes of cooperation or collaboration. We also want to be able to design algorithms that allow us to handle those flexibly sized groups. And we want to be able to compose software as we get out to a macro level. We want to be able to compose software that works across the software boundaries that are implied both by these groups and maybe the software boundaries that we have come to know previously, and I'll talk about those with respect to CUDA. One of the things that I want to call out immediately on this slide at the beginning is the idea of a grid-wide sync. This is a concept that is perhaps the most radical in terms of all of the ideas that we're going to present. And it may not be immediately obvious why that's radical. You really have to drill into the CUDA execution model to understand what were some of the hazards associated with trying to do this previously if you didn't have this methodology. And so the grid-wide sync is something that is very useful, I believe, for a lot of different kinds of problems, and I'll spend a little bit of time hopefully talking about motivation for grid-wide sync towards the middle or the second half of this presentation. But I believe that if I were to just pick one thing out of this presentation to be the most interesting or revolutionary or something that you might want to tuck away in your CUDA programming toolkit, it might be the idea of a grid-wide sync, because I think as you get to be an adept CUDA programmer, you will start to take on challenges, CUDA programming challenges, where you will immediately recognize the need and the benefit for having a grid-wide sync, which was mostly absent, as we'll see, from the CUDA programming model, with one exception. So this methodology, or these methodologies, creation of groups, creation of flexible algorithms that work with groups, it should be widely applicable, I believe. And we'll talk about a couple examples of this as we get through the various phases of our presentation today. I'm listing a few examples there on the right-hand side. And we'll see examples of those as we work through the presentation. So just to level set, where have we been? Up until now, we haven't really been exposed to the idea of cooperative groups in this sequence or in this series so far. And so what the mechanisms or the methodologies available to us as a CUDA programmer up to now, up to, let's say, the introduction of CUDA 9, were somewhat limited. And really the one that we'll focus on here is the idea that we had the ability to do block level, within a block, cooperation of threads. Remember, cooperation here, I'm referring to two fundamental building block ideas. That is the idea of synchronization or execution control, as well as inter-thread communication. And we observed that at the block level, we have a basic building block called sync threads, which provides a level of execution control, which is block-wide. It is logically at the block level. It doesn't extend beyond the block level. It is not any less than the block level either, so it's exactly the width of our thread block. And coupled with that, we learned about using shared memory for inter-thread communication, and most of that we learned in modules 1 and 2. Later on, I believe it was in module 5, we learned about warp shuffle. This is another form of inter-thread communication that exists within the CUDA programming model. It doesn't depend on shared memory per se, but it also is effectively limited to the thread block level. In fact, it's limited to the warp level, but it certainly doesn't extend beyond the warp level. So before CUDA 9, or up until now in this series, we've really only had a relatively limited set of functionality that we can use to allow threads to cooperate, and that functionality has been almost completely restricted to operating at the block level. So what we're going to introduce is a set of methodologies, a set of APIs, if you will, that are going to allow us to have more flexibility at the thread block level, as well as to go beyond the thread block level. And when we go beyond the thread block level, we'll talk about grid-wide groups and synchronization associated with that, and then we'll even spend a small amount of time talking about a multi-grid synchronization methodology, which basically extends the idea to multiple devices operating in the same machine. And so we're going to introduce, as you see depicted on this slide, we're going to introduce some new programming constructs, basically C++ objects, C++ classes that are going to allow us to access this functionality. You can see some of the examples here. We're going to get into this API, if you want to call it that. We're going to get into that in a little bit more detail in the next couple slides. But one of the things that I'd like to point out is that there are some requirements for using, or some, let's call them requirements for using cooperative groups. First of all of the cooperative group functionality is contained within a cooperative group's namespace, and you can see example of the namespace name down there at the bottom of the slide. Therefore, when we want to use things like coalesced threads, or if we were to call out a named group specifically, a named group type specifically, we're using auto here, but we'll see some named group types here in the next couple slides. If we wanted to use this kind of API, we would normally have to use cooperative groups with that scope resolution operator as I've depicted on the bottom when I'm referring to the namespace. And so that's a requirement for your code as well. One of the things that you'll commonly see in cooperative groups code to simplify the code is to use some construct like using namespace cooperative groups, which opens up the namespace so that we don't have to use the scope resolution operator tediously every time we refer to one of these. But you should be aware of that fact that you're going to need to provide some mechanism like that. And for most of the slideware that we have here today, we're going to assume something like that is in effect so we don't have to have the scope resolution cluttering up all of our API calls. There's some other requirements as well for cooperative groups, and it will vary depending on what level of cooperative groups that you're using or that you want to use. In particular, the requirements get more significant when we start to talk about a grid-wide group or a multi-grid group. So those have specific both hardware as well as environmental requirements. And when we get to that point in the presentation, I will make what I hope is a fairly simple suggestion for validating that you have a correct environment for wanting to use that functionality. One thing I will point out is that for the grid-wide group and the multi-grid group, that does require specific kinds of hardware support, and that hardware support was introduced in the Pascal generation of GPUs. So if you're trying to use a GPU prior to the Pascal generation, you wouldn't have access to that. Of course, Summit and Cori have Volta GPUs in them, so no issues there. All of this functionality should be available. This is, as I mentioned, a construct that is built at least partly based on C++ objects, and so we're going to introduce the idea that there is a base group idea or a base class that is being inherited from. That base class is called thread group, and all of the groups that we're going to talk about are actually inheriting from that base class. This inheritance isn't terribly important for us to really understand as programmers. However, it serves a number of useful purposes, one of which is that it allows for a fairly harmonious and straightforward way to build the API. And so what we'll see is that when we're interacting with these groups, some of the functionality that we may want to use, which is common across groups, like the ability to synchronize the group, for example, will be accessed in the same way. And one of the ways that that's provided for as well as enforced is through this object inheritance mechanism, which is underpinning the way this technology or this capability is being delivered. It's not that important to understand that much about the classes. I like to refer to the classes mostly as opaque, and we're going to interact with them through their public methods primarily. So what are those public methods? The first set of methods that I'm depicting on these slides are actually provided by the base class thread group, and therefore they're available to all the groups that we're actually going to be interacting with or using. We won't really be using the thread class directly. However, as I mentioned, one of the methods provided is the sync method, and so this is provided to synchronize the threads in the group. And if you wanted to associate with this with something that you've already learned, you could associate it with the idea of the sync threads intrinsic or built-in function, which we learned about, I think, in Module 2. And the sync threads function synchronizes threads across a thread block. It's an execution barrier primarily. And the sync method works the same way, except it's going to synchronize the threads within the group as opposed to some other definition of a collection of threads. A couple other methods that we might be interested in, for example, what is the size of this group in terms of the number of threads? We have a method that provides that. Thread rank is a method that will provide for a given thread that is executing it, it will return a unique number within the group. So if I have a group of 4 threads, then I can expect that if each of those threads executed the thread rank method on their group, that each of them would receive a value from 0 to 3, 1 per thread. In other words, a unique value. This is sort of related to the idea of thread idx.x, let's say, if we were working within a thread block, but it's not really a completely identical idea because thread idx.x will be unique across the thread block, whereas thread rank is only unique within the group. The last general method at the base class level is this method called isValid. We're not really going to spend any time at all in this presentation on this. However, just to give you a basic idea of what's going on here, it is possible to misuse this API. In other words, to ask the API to do things that are not legal. And I'll try and remember to point one example of that out when we get a couple slides into it. When you're working with device code, there's not necessarily a typical error mechanism that we might experience when we're working with host code. So we're not going to typically witness a seg fault when we do something illegal in device code. And device code doesn't have a well-defined concept of throwing exceptions. Not to say that it can't be done in any fashion, but it's not the same way that you would expect as if you had a try-catch mechanism in C++, for example. And so one of the things that could arise is that you may ask the API to do something that is not valid or legal. And I'll point out, I think, one example that I can think of in a couple slides. This method then gives you an idea of whether or not this group that you have formed is a properly formed group or not. It's not something that I see a lot of usage of, but there may be situations where you might want to use this if you think that the way that you're performing a group creation could possibly be exposed to a hazard. As we go to different groups, we may discover that those different groups, in other words, the groups that inherit from the base group, the groups that we're actually going to use, like thread block will be an example of a group that we're actually going to use. As we go to these different groups that we're actually going to use, some of those groups will have additional methods, and in particular, thread block has a couple of additional methods. The group index method, which provides a 3-dimensional block index within the grid. This should be immediately familiar to you. It's essentially an analog a duplication of the idea of block index dot x, y, and z. And the three-thread index would be exactly the same thing for a thread block group, which is completely analogous to a thread block the way that we thought about a thread block. And so the thread index method will return a three-dimensional index, which should be exactly analogous to thread index dot x, y, and z used within a thread block. So let's start to talk about how we might use this. First of all, we're going to start at a higher level in terms of collections of threads and work down to lower levels in terms of groups of threads or partitions. So when we launch our kernel, we have the idea of the grid. That's the set of all threads that are launched in the kernel. And we know that our grid is broken logically into thread blocks. Thread blocks are groups of threads which execute together collectively on a single SM. And a thread block is a logical construct, and it has various things like the built-in variables that we talked about and so forth. Therefore, I can create a group that consists of the thread block that I am currently in, and that group would be called a thread block group, so it's a named group type. And I have a making function for that called this thread block, and that assigns a object to this opaque variable g, and we can then interact with that variable g using the methods that we just talked about. And so this thread block will create a thread group that is in every way analogous to the thread block that you've already learned about in CUDA. It has the same composition of threads, it has the same logical identity, and so forth. Once I have all the threads in the thread block, I might decide that I would like to subdivide or partition those threads. And so, or I should really say partition that group. And so what I can do is I can have another making function called tiled partition, which takes two parameters. The first one is the group that I would like to subdivide, and the second one is the width of the subdivided group, or the subdivided tile, we could refer to it as. And so in this first example on this slide, when I called tiled partition on G of 32, what I'm saying is take this group, which I have previously defined called G, which we know is a thread block level group, it's the entire thread block, and break it into tiles of 32 threads each. Now, we know as CUDA programmers, based on what we've learned already, that that should probably correspond to a warp, or the warps that are associated with that thread block. Within cooperative groups, there isn't really an explicit idea of a warp. In fact, the warp is an idea that is only mildly exposed in the CUDA programming model. When you get to some intrinsics, built-in intrinsics like warp shuffle and so forth, you will see the warp exposed at the API or at the syntactical level. But largely, warp is an idea that's more or less hidden from the view of the CUDA programmer in the CUDA programming model. And it's hidden here as well. So you as a CUDA programmer have good reason to believe that when I break this group called a thread block into a set of tiles, each of which is 32 wide, that each of those corresponds to a warp, and that is the case. But nevertheless, we don't need to have that assertion in order for this methodology to hold together. Why do I spend time on this? You may have noticed that, especially with the introduction of CUDA 9 and the Volta family, that we're starting to break some of the old mechanisms that we had which were strongly warp-oriented. Even the execution model, the underlying hardware execution model with the Volta family of processors has deviated a little bit from the execution model that we had prior to Volta. Therefore, it's reasonable to assume that a strong dependence on the idea of a warp, which is largely an artifact of machine design, it's largely an artifact of hardware execution, and it's not a strongly represented idea in the CUDA programming model, is something that we may want to move away from. And I'm going to suggest to you without proof that that's part of the idea here, is that with the cooperative groups, we're moving, again, a little bit. We're not depending on the idea of a warp. We're suggesting that a group has a characteristic and behavior defined by cooperative groups, not anything else. Nevertheless, underneath the hood, you can be certain at this point in time that this kind of tiled partition, breaking it into groups of 32, is breaking it along warp boundaries. And probably as we go through this, you'll see why that's probably the case. Anyway, we can break our grid group, our block level group, thread block group, into tiled partitions of 32. And then as we're depicting again on this slide, we can further subdivide that using the same making function. We pass now the group called tile 32, and we break it into tiles that are of size 4. And those tiles of size 4 are now logically referred to using the tile 4 handle or variable name. And this allows us to work individually in tiles of 4, or at the same time, using a different group, we can work with the tiled partition of 32 called tile 32, or at the same time, we can work at the thread block level using the group G. All of this is something that we can intermix in our code and use as needed. Now, there's one other thing I want to point out on this slide, and that is that this methodology that we're depicting on this slide is what we're calling program defined. That means that the second number that we're passing in the tiled partition maker, for example, the number 32 or the number 4, can be variables. They can be defined at runtime or modified at runtime. They don't have to be known at compile time. They don't have to be known as constants. Okay? And that's part of what we mean by program defined. So these are groups that you can effectively create at runtime, and even the width of the tile, if we're doing a tiled partition, even the width of the tile can be declared or defined at runtime. Okay? Another thing I want to point out is that number that we pass, 32 or 4, as the examples depict here, has a limited set of values which are legal. Those limited set of values are that it has to be less than or equal to 32 currently. That could change in the future, but today it's restricted to values that are less than or equal to 32, and it's also restricted to values that are a power of 2. Okay, and so the fact that it's restricted to values of 32 or less might give you, again, an inclination or an inkling that this might somehow be leveraging warp methodology under the hood, and I would not disagree with that, but that is not something that is a necessary part of the cooperative groups construct. There's a question in the chat that says, do the tile 4 operations then correspond right now to sub-warp SIMD? I think I would answer that question with yes. In other words, certainly a tiled partition, which consisted of 4 threads, is something that's less than a warp. And as we'll see, if we do any operations on those operations are happening at the sub-warp level. What I'd like to do is defer any further discussion of that question until we get to our next couple slides, because as we'll see, there's some more interesting capability that we want to expose, which is going to get directly at the idea of performing specific operations at, I'll just repeat the terminology, at the sub-warp level, or at a group level that's less than 32, at a tile level of less than 32. So with that introduction to the basic syntax of group creation, one of the things that enables now is what we can refer to as generic parallel algorithms. In other words, an algorithm that can take a group and behave in an intelligent or give predictable behavior or expected behavior more or less independent of the group size. And so we already covered the idea that let's say our tiled partitions, but we can extend this even to the thread block level group, does not matter. These are all entities that inherit from the thread group object type or the thread group class. It does not matter. But if we were talking about whether we're talking about the thread group or any of the subdivisions of the thread group, we'd like to be able to write a generic parallel algorithm which could take any of those kinds of group divisions or group levels and work in a sensible fashion. And so what we're depicting on this slide is a device function called reduce, and hopefully you have an idea of what that might do. It's not unlike the reductions that we talked about in Module 5. We want to take a set of threads, each of which has a value, and we want to do some sort of reduction of those values. In this case, we're going to be talking about a sum reduction. So the idea is each thread has a value, and we'd like to produce a sum of that value across all the threads. And in this case, for generic parallel algorithms, we'd like to be able to do that correctly and independently of the group size. And so what we can do is we can write a code as depicted on the bottom. We'll walk through that in just a moment. But as a result of having a device function like that, which takes a thread group, then we can call that device function at the block level, as we're depicting on the upper left, or at the warp level, or at some other subdivision tile level, as we are depicting on the right. So how this would work then is we see that the reduce function takes, first of all, a group as its first argument. The second argument is a pointer to the type of data that it's working on. And this pointer, as we'll see, is intended to be used for a resource that's going to allow for inter-thread communication. And so the way that you would use this function would be to pass a pointer to shared memory for the int x argument, int star x argument. And then third is the value, which presumably is per warped or per thread across the group that you want to reduce. And so the first thing that we're going to do is declare a variable called lane, which we're going to extract directly from the thread rank method. And the lane variable represents a unique number, 0 up to however many threads are in my group, so that each thread has a unique lane identifier. And then we're going to do what is basically what I would call a fairly typical shared memory sweep style reduction. And so this is something that we introduced in Module 5. It doesn't look exactly like what we've described there because, of course, first of all, we're using cooperative groups. But it should be reminiscent of what you saw there. So we have a for loop which is subdividing its size. It's starting out at half the thread block and then dividing the size of the activity by 2 each time. And at each pass, it is loading a value into shared memory, and then it is using shared memory to perform inter-thread communication so that we can sweep the higher values into the lower values. And if we do this in a binary sequence or a power of 2 sequence, then we end up with the reduced value in lane 0 in this case. You'll note also that we're using one of the methods g.size. This allows us to have behavior that's independent, more or less, of the thread group size. And remember, we restricted our thread groups to power of 2 sizes. That was important. At least for the tiled subdivisions, we restricted those to power of 2 sizes. That was important because we're using a power of 2 subdivision sweep strategy here. And we're also using the .sync method to provide the necessary synchronization so that we can guarantee that all threads in the group are doing these steps in sequence, in proper sequence. So this should be hopefully reminiscent of the parallel sweep reduction that we saw in Module 5, except now we have recast it to take advantage of cooperative groups, and in the recasting we now have an algorithm that works flexibly across different kinds of thread groups that are passed to it. Can the pointer X point to global memory or only shared memory? That's a question in the chat. Normally, trying to do reductions out of global memory has a variety of hazards associated with it. And that generally depends on the breakpoints of the thread blocks. That's one of the main hazards that you would run into. I would have to think carefully, but I believe that it should be possible to point to global memory. And one of the reasons that I say that is that, as we know, sync threads, we may not know, but I'm telling you, sync threads is not only an execution barrier, it's also a memory barrier. And so the sync threads call function, built-in function, first of all, serves to synchronize the execution of all threads in the thread block, but it also acts as a shared and global memory barrier, which means that visibility of results accumulated prior to the sync threads call are visible to all threads after the sync threads call. And I'm now talking about the thread block, the old style of CUDA programming. The same statements are true of the sync method here. It is not only an execution barrier, but it is also a visibility barrier. And I'm pretty sure, I know that it is a visibility barrier within the thread block for shared memory. And I'm pretty sure it's also a global memory visibility barrier as well. So it should be possible to use this with global memory. I wouldn't really recommend that for performance reasons, but I think it should be possible. Okay. Actually, before I leave this slide, let me just point out that based on the last 2 or 3 slides, the first homework assignment is basically just going to explore these in some detail. And if you, so the first homework assignment will walk you through the steps of creating a thread block level group and then subdividing that group and then looking at the behavior of subdivision using this exact reduce function. So you'll see how it works at varying group sizes. Now, everything that we've talked about so far has been predicated on the idea of program-defined decomposition, meaning we could pass those numbers like 32 or 4, in other words, the tile size. We could pass those numbers at runtime. They didn't need to be compile time constants. However, we have an alternate version of the API, basically templated version, and the template parameter is the tile size. And you can see that depicted on this slide. So if I can create a tiled partition of tile width 32. I can take my thread block and subdivide it into a tiled partition with a width of 32 using this templated version. This is obviously something that is known at compile time. And as a result of that, I don't have to pass a parameter, an ordinary argument to the function, the tiled partition making function. I don't have to pass a tile width size because it's passed as a template argument. This also creates a set of tiles of size 32. However, this is known at compile time, and as a result of this, or whether I was doing 32, 16, 8, 4, 2, or 1, these are known at compile time. And as a result of this, an important benefit is that we have some additional functionality, new methods that are available to us. And these new methods might, again, be reminiscent of things that you've learned about already. So some of these new methods, as depicted in the center column there, are the shuffle methods: shuffle, shuffle down, shuffle up, and shuffle XOR. We learned about warp shuffling in Module 5. And this is a closely related concept. This is shuffling using the same ideas, except it's shuffling happening within a thread group. And these, as I mentioned, this functionality is now available because we've chosen a known at compile time subdivision of the group, whatever the group may be. There's some other functions there that you may be less familiar with. Any, all, and ballot. Those 3 are in a group of functions that we really haven't talked about. Those are called warp voting functions. And the last 2 functions there, are match any and match all, are in a category of functionality called warp matching functions. And the matching functions could be thought of as a type of a warp level reduction built into a single instruction or a single intrinsic. All of these intrinsics, whether it's shuffle or the warp voting functions, are available as built-in functions for what I would call ordinary or non-cooperative groups programming, and you can read about those in the programming guide. But we are now exposing that kind of functionality that operates at the group level. So now that we've gotten to this slide, I want to go back to the first question and say that yes, these operations like shuffle, shuffle down, shuffle up, shuffle XOR, for example, are warp level operations, are operations that we had previously learned about at the warp level, which can now operate at a sub-warp level. There's actually no real magic here. If you go back and study the warp shuffle operations carefully with the parameters that are available to you to specify, you can get those operations to work at a sub-warp level. It requires some extra effort by you as a programmer compared to just letting it operate warp-wide. And so there isn't really that much magic what's going on here. However, a lot of the complexity and a lot of the boilerplate is hidden by the fact that once I have specified a group of a particular size using this templated methodology, this known at compile time methodology, then I have access to this functionality and it's ready to go at the group level. I don't have to do any extra work with masks or other parameters that define which threads I want to operate on. An additional possible benefit here is because this is a size known at compile time, it may result in faster code underneath the hood than using the program-defined methodology that we talked about already. So when I have this statically defined tile or statically defined subdivision of a thread group, then my function probably would look a little bit different. The group that I'm going to pass is now going to be templated, or my reduce function will now be templated for the group, the templated group type that I pass to it. And in this case, what we're demonstrating is, rather than a shared memory style sweep reduction, we're demonstrating a shuffle-based reduction. And so we also talked about the idea of how does a shuffle reduction work in Module 5. And so this is essentially working in the same way. And we observed in Module 5 that the shuffle-based reduction had some, in some ways it was simplified. It didn't depend on shared memory, for example, and it allows for direct thread-to-thread communication without an intervening vehicle like shared memory. And so in this case, we can write a very nice, compact group tiled partition reduction operation. And we don't even need the synchronize operation because of the nature of the shuffle operation itself. Since there's another question in the chat, since these are no longer compiler intrinsics, is it likely that this kind of functionality could be standardized across accelerator programming models? Well, I'm going to suggest that, at least on the last couple slides, the last one and this one, that most of the methodology that we've talked about here is probably something that you as a CUDA programmer could directly map to intrinsics that are defined in the CUDA programming guide and the CUDA programming model. So I don't think that, at least as far as we've gone here, that we've really deviated much in terms of implementation from compiler intrinsics. However, at the way that we're exposing it here, I would agree that this is not a compiler intrinsic. What we're exposing here is a set of methods associated with classes. The implementation of that is something that may ultimately depend on compiler intrinsics, or the same kinds of intrinsics we would use as a CUDA programmer. With that proviso, I would say, yes, it's likely that this kind of functionality could be standardized across accelerator programming models. Whether or not that actually happens or not, I can't say, but certainly NVIDIA is actively working with language standards bodies to build parallel algorithm support in a most straightforward way into standard language definitions like C++ 17 and beyond, for example. I'm not suggesting that that's exactly using cooperative groups or methodology like we've described here, but nevertheless, it's something that you could imagine, I think. Okay, so let's shift gears now because we've done enough, for the moment, we've done enough investigation of the decomposition and the establishment of tiled partitions, the creation of groups, thread groups at the block level, basically, and the decomposition of those groups and the creation of tiles and the manipulation of tiles and creating parallel algorithms. So we've covered much of the ground that's associated with things that are happening at the thread block level. We're actually going to revisit one more idea. So the idea of coalesced groups at the end of this presentation is also something that is essentially associated with the thread block level, or you could even say it's associated with the warp level. But we're going to shift gears for the moment and switch our thinking now to what's happening at a higher level than the thread block. And as we mentioned, hopefully there might be some motivation for this. If we talk about what are the ways that we could synchronize all of the threads in a grid, in other words, across all of the threads associated with a kernel launch, we don't really have any explicit mechanisms in CUDA. There's an implicit mechanism that's existed from day one, and that is the kernel launch boundary. What I mean by that is, when I launch a kernel, once I know that the kernel is complete, then I can be certain that all of the threads have reached a synchronization point. All of the threads have finished the work that was associated with them as a result of that kernel launch. And so the kernel launch boundary, if you will, is a synchronization point. And if you've written any sort of complex CUDA algorithms, you might have already used this methodology, consciously or unconsciously, to break your work into pieces to guarantee that a piece of work associated with a particular activity is complete before you release a group of threads to go off and process the next piece of work. In other words, there's presumably a dependency. And so when there's a dependency on a large scale from one set of threads to the work accomplished by another set of threads, you as a CUDA programmer might have logically broken those into two kernels, launch one kernel, then the other kernel, in order to satisfy the dependency, and in so doing, you were implicitly using the kernel launch boundary as an implicit grid-wide sync. That was really the only thing that existed. But wouldn't it be neat if we could do that within the grid? In other words, within a single kernel, wouldn't it be interesting if we could have a barrier, let's call it an execution barrier, if we could have an execution barrier that would require all threads to meet that barrier before any threads could go beyond the barrier? Wouldn't that be interesting? And hopefully that might already seem interesting to you without much development of the idea. But if you would like to have some more motivation, we're going to get to that. Hopefully I'll give you some more ideas as to why this might be interesting. But for the moment, let's talk about the mechanism and the syntax. So the first thing to note is that we're going to invoke this grid sync, and we're going to create the group in a fashion similar to what we've learned about already. We're going to have a named type called grid group, which presumably inherits from thread group that we mentioned already. We're going to have a variable name called grid, and we're going to have a making function called thisGrid, which is going to now assign some sort of relatively opaque object to the variable grid, or the object grid. And then we're going to interact with that using its methods. And really the main, and I think the only method that we're going to care about for this discussion is the sync method. That presumably works the same way as the other sync methods that we talked about. In other words, all of the threads in the group must meet that barrier before any are allowed to proceed beyond the barrier. That's at the device code level, that's the way that we're going to use this. And the other important change is that we can no longer use the triple chevron syntax to launch this kind of a kernel. Okay, so the way that we've been launching kernels from day one in this course is to use the triple chevron syntax, where we have the function name or the kernel name and then the triple chevrons, which give us basically the grid configuration parameters, and then we have the list of arguments. We're not going to use that methodology. We cannot use that methodology. If we attempt to use that methodology, it will not work. In fact, what will happen is you will think everything's working because your program compiles and it appears to run, but what's happening under the hood is that if you launch this kernel that way with this grid sync in it, using the triple chevron syntax, what will happen is the grid sync barrier will be silently ignored. Probably you don't want that. So you need to remember that when you're going to use the grid group methodology, as we're depicting now, talking about now, you're going to have to dispense with the triple chevron syntax, and you're going to have to use a new CUDA runtime API call called CUDA launch cooperative kernel in order to launch that kernel. Now, I don't really want to unpack the call right now for a couple reasons. I'm going to unpack a similar call when we get to the grid group. When we get to the multi-grid group. So I'll unpack a similar call just to give you an idea of what's in it. But it's basically just a bunch of syntax. You probably won't remember it until you need to use it. And once you need to use it, what I would like to suggest is that you go to the programming guide, because the programming guide, not only does it have the syntax, but it also has some nice little bite-sized pieces of functions which are going to accomplish a bunch of useful things for you in the process of launching a cooperative grid. And I'm going to talk about some of those things right now. First of all, the device, when I want to launch a cooperative grid using this new API called CUDA launch cooperative kernel, the device needs to support the cooperative launch property. What is that? Well, it's a property like other device properties. And how do I typically get device properties? I use a particular call to do that, and that call is nicely detailed in the CUDA device query sample code. Okay, so it's called CUDA get device properties, I think, or CUDA device get, no, it's CUDA get device properties, and it returns a struct full of interesting information about the device that you're running on. So there's a question in the chat now that says, which device compute capability starts supporting cooperative launch? The device compute capability that starts supporting cooperative launch is 6.0 and higher. Now, having said that, That is not an across-the-board statement. What I mean is there's more to support a cooperative launch than just having a compute capability 6.0 device or higher, 6.1, 7.0, 7.5, Ampere 8.0, these all support cooperative launch, so 6.0 or higher. However, that is a necessary but not a sufficient condition. And so what I'm going to suggest is that you query this cooperative launch property. The general methodology to do that is similar to the methodology that is depicted in the device query sample code. But to get at a much nicer, succinct version, I'm going to suggest you go to the Cooperative Groups section of the programming guide, because they've got a nice little 3-line thing that you can just copy and paste and drop into your code. You're done, and it's taken care of. You now have extracted this property, and then you can now condition your code behavior on that. Okay? And another reason that I want to reinforce this way of thinking is because I don't want you to think that, hey, I've got a 6.0 device, it will just work, period, end of story, because that's not true. Okay? Probably in most cases it will work, but if you have a CUDA 6.0 device or a CUDA 6.1 device, a compute capability 6.1 device, for example, that happens to be in your laptop and you're doing development in a Windows environment, it's not going to work. Okay? Because there's more requirements for cooperative launch than just compute capability. That's one of the requirements. It's not all of them. So rather than trying to go through what are all the requirements, I'm going to suggest, because it's good programming practice, that in your program you query the cooperative launch property before attempting to use this functionality. Okay? Now, another requirement of a cooperatively launched kernel has to do with the total number of threads or the total number of thread blocks that you launch. And this is going to take a little bit of time to unpack. It might not be obvious, but one of the things that we're going to need, looking at the code on the slide, the device code, the kernel code on this slide, is we're going to need that every thread in the grid should be able to reach that grid sync barrier. If for some reason a thread cannot reach that grid sync barrier, your code is broken. Now, one of the obvious ways that I could prevent a thread from reaching the grid sync barrier is if I created some sort of conditional construct and prevented threads from reaching the barrier that way. That would just be illegal coding, right? So first of all, from a code construction perspective, you don't want to do anything that would prevent a thread from reaching a grid sync barrier if you're intending to do a grid sync. Every thread is going to need to get there. However, there's a less obvious requirement, and that is that all of the threads have to be schedulable. In order for a thread to be able to get to this grid sync barrier, it needs to be a thread that can be selected, that can be distributed or deposited by the CUDA work distributor onto a SM, and it needs to be schedulable from that SM so that that SM can pick up that thread and move it along from time to time. In other words, the thread needs to be able to make forward progress. Now, what does this mean? Let's go back to the way that we thought about creating our grids from day one. One of the first methodologies that we learned was a thread strategy that says, I'm going to assign one thread per output point. And this actually works pretty well for a certain class of problems, and there's really not too much wrong with it. However, when we do that, we might create an arbitrarily large grid. If I have 1 million points in my output data set, I'm going to need 1 million threads. If I have 1 trillion points, I'll need 1 trillion threads. No problem. It works just fine based on what we've learned so far. However, if I create a grid with 1 trillion threads, not all of those threads will be able to actually use up an execution engine on the GPU at any instant. Okay, and so now we're going to have to start talking about ideas of occupancy and something that I refer to as the instantaneous thread carrying capacity of the GPU. We've already talked about occupancy already in one of the previous sessions. We had a slide on occupancy. And we've already talked about the idea of how many threads can be scheduled on an SM already. That was a topic that we unpacked in Module 3. And we learned that for many SMs, for most SM designs, Turing being an exception, but for most SM designs, you can have up to 2048 threads per SM. That's the maximum thread complement that can be on that SM. And as we know, a GPU is composed of a number of SMs. And so if I have 2048 threads per SM maximum, and I have, let's say, 10 SMs in my GPU, then I can have a total complement of threads of 20480, 20,000 threads, that can be actually schedulable. In other words, that the warp scheduler on an SM could pick up that warp that thread belongs to and put it into execution. Now, if I launch 1 trillion threads across a whole bunch of thread blocks, not all of those threads will be able to be deposited on SMs at the same time. And this, for the types of methodologies that we've been using so far, no problem. As a thread block retires, in other words, finishes its work, it leaves the SM and the CUDA work distributor picks up another thread block that's waiting in the queue and deposits it on that SM. And this is basically the stream-oriented execution model of the GPU, okay? And there's nothing wrong with that, and that's basically the first kind of kernel grid description that we ran into. Later on, we talked about things like a grid stride loop, another way of arriving at a grid of threads to do my job. But if I have blocks that are sitting in the queue that are not yet deposited on an SM, there's no way the threads in those blocks can make forward process. There are no execution resources assigned to them at that point in time. And if all of my SMs are completely loaded with thread blocks and all of those threads have reached the grid sync barrier, and I've got a bunch of blocks that are sitting in the queue waiting to be deposited, therefore their threads have not even started executing yet, I'm going to run into a deadlock. So another requirement of a cooperatively launched kernel is that the grid size cannot exceed a certain level. This is closely related to occupancy for some of the reasons that I already discussed. Occupancy asks and answers the questions how many threads can actually run on an SM according to my kernel design and according to the actual SM that I'm running on. That's fundamentally the question that occupancy asks and answers. And if I know that, then I know that the sum total of all those across all of my SMs, which is just multiplying it by the number of SMs, is therefore the total number of threads that I can have in flight, that are actually able to execute, that are actually able to be scheduled, that are actually able to make forward progress, that could reasonably reach a grid sync barrier. Therefore, that occupancy, when considered device-wide, presents an upper bound for my grid size. Okay? Now, this is a fairly complicated topic if we go through every last detail, and it's why I've shied away from trying to discuss occupancy at great lengths. But you should know that occupancy has an API associated with it. In other words, we can programmatically ask the CUDA runtime to say, what level of occupancy can I achieve for this kernel? In other words, how many of these blocks that I have defined in my kernel can be resident on an SM at the same time? Once I know that value, which is returned by the CUDA runtime API call depicted at the bottom of this slide, then I can size my grid based on the number of SMs in my GPU, which is also runtime queryable. I can size my grid by multiplying those two numbers together. The number of blocks per SM number that's returned by the API call at the bottom of the slide, times the number of SMs in my GPU, which is also runtime or device queryable. And that then presents the total number of blocks that I can launch for this kernel in order to satisfy the requirements of the cooperative grid. Okay? So that's a necessary requirement. And having gone through all that, what I would suggest is you could either look at the homework, because I'm going to show you an example of this in the second homework exercise, or you could go to the programming guide, because there's a nice, it's not 3 lines of code, now it's about 8 lines of code, but there's a nice 8-line sequence that you can pick up that'll do all this for you. Okay? You can literally just basically copy and paste that into your program to get started with this idea of doing an optimally sized kernel launch. Okay? Now, having said that, the whole idea that we just discussed there, using a set of APIs to determine what size of a grid I'm going to launch, pretty much rules out the first grid sizing strategy that we talked about. It pretty much rules out 1 thread per output point. Because if the number of output points exceeds the number of threads that I can run on the GPU, and let's say I don't know what GPU I'm running on yet when I'm writing my code, if the number of threads happens to exceed that, then that methodology simply doesn't work. However, the grid stride loop methodology that we discussed in, I don't know, I think it was module 5, the grid stride loop methodology dovetails nicely with this, because now I can size my grid according to the runtime calculations that we just walked through. And then based on that grid size, I can create a grid stride loop, which gets all of my work done. So these ideas are all relevant to each other. So there is a question in the chat. So if 2048 threads within an SM call sync, they cannot be scheduled out of the SM. That's correct. Once a thread block is deposited on an SM, it lives there forever until it retires. In other words, till the threads reach the end of their code, the return statement, if you will, although there typically wouldn't be a return statement, the end of the code. So yes, it's basically guaranteed by the CUDA programming model that once a thread block is deposited on an SM, it will stay there for its lifetime. There's a couple exceptions to that. One exception is debugging. Another exception is dynamic parallelism, which we have not talked about at all in this series. But if we leave those things aside, that guarantee pretty much holds, that once a thread block is deposited in SM, it will stay there forever. And even those other cases, the debugging case and the dynamic parallelism case, and there's also the preemption case. But if we consider those three cases to be special cases, let's just say that those special cases are handled by mechanisms within those areas of activity. So in the debugging case, the fact that a thread block could be evicted from an SM is handled by the debugger. In the dynamic parallelism, the same thing is handled. There's a context save and restore that goes on. And I'm going to just sort of arbitrarily say in the preemption case that's also true. So it's basically guaranteed for the purposes of our discussion here that if an SM or if a thread block is deposited on an SM, then all of the threads will remain on that SM and will remain schedulable for their lifetime. Okay. So that is the grid group, and now what I'd like to do is shift gears a little bit and talk about some motivation, and then we'll talk about the multi-grid group, and then we'll talk about our last topic, which is Coalesced group. So I probably won't cover all the ideas depicted on these slides. I'm going to work actually from right to left, and let's talk about, on the right-hand side, particle simulations. So one of the motivations for grid group is kind of what I described already. We might have a situation where I have groups of activity that are dependent on each other, and so a particle simulation might be an example of that. If I have an n-body or particle simulation, I might have phases of calculations that I need to do, let's say iteratively or per time step. And those phases of calculations might be things like, first of all, I need to take the constellation of bodies and I need to compute all of the interbody forces. And then once I compute all of the interbody forces, then I can start to compute the body-by-body motion trajectories on a per time step basis. And then once I've computed the motion for this time step, I might want to do something else, like maybe see if any particles have collided with each other. And I might need to have all the motion calculations complete before I can do the collision calculations, for example. So those things have a dependency on each other. I might need to do step 1 before I do step 2. In other words, I might need to do step 1 in its entirety before I do step 2, and I might need to do step 2 before step 3, and so on. When I have a situation like that, of course, the way that we would have handled that is to write 3 different kernels if they were that kind of dependency relationship, and then I would call those 3 different kernels iteratively in my time step loop. However, there might be some benefits to not having to break things up into 3 different kernels, and I'm going to talk more about that in a moment. And so with the grid-wide sync, I can now think about the idea of merging all of that activity into a single kernel, the 3 different phases of activity, and then just calling that single kernel in a loop per time step. Let's move to the center, and I'm going to talk about a couple ideas now with the center. First of all, what I'd like to do is introduce the idea of specialization. So the idea behind specialization is that when I think about a problem like vector add, for example, every single thread in my grid is doing the same thing. They're just taking an element from vector A and an element from vector B and adding it together and storing it in the appropriate location in vector C. But do I really have to have all of my CUDA programming work that way? No. One of the ways that I can deviate from that is I can have something called specialization. The idea behind specialization is that some subset of my grid does something while another subset does something else. And one of the logical partition points that I could think of is breaking things up by warp, in other words, within a thread block. So I could have one warp doing activity A while the other warps are doing activity B. Or at the grid level, I could have one thread block doing activity A while the other thread blocks are doing activity B. Both of these are perhaps interesting and useful in certain scenarios, and it shouldn't be that difficult for you to imagine as a CUDA programmer how you might do that. Let's take the thread block case. I have the idea of a thread block identifier. That's my block index. And so if I have a block index that's unique across all of the blocks in my grid, and I could designate one block to do activity A simply by having an if construct or perhaps a switch case, some sort of conditional construct, to say that if my block index is such and such, then I'm going to do A. Otherwise, I'm going to do activity B in this block. And that would be a way of doing something called specialization at the block level, or block specialization. You could also extend that idea very straightforward, in a straightforward way, to warp level specialization. So if you can come up with an idea of a warp identifier, a unique ID per warp in my thread block, or even in my grid, but let's say a unique identifier per warp in my thread block, then I could condition my code based on my warp identifier. If I'm in warp 0, I do A. If I'm not, I do B. And so once I have this kind of specialization or partitioning, I can think about creating algorithms that work in a fine-grained way using ideas that you may have heard of, things like master-slave or producer-consumer. In other words, a set of code that has really two different things going on, the master activity and the slave activity, the producer activity, the consumer activity. And so this is also related to an idea of persistent kernels. The idea behind persistent kernels is that normally I think of a kernel doing a fixed quantity of work and then I'm done. It exits, it returns. However, that isn't the only way that I could design CUDA code to run and behave. I could design something called a persistent kernel. In other words, a kernel that sits there and runs forever. Not actually forever, but for a very long period of time. And the way that I might feed work to that kernel might be through a queue. And so the kernel is sitting logically at one end of the queue, and it's looking to see when queue items are ready, and when they do, it takes those queue items and then begins working on those, perhaps distributing. If I have a master entity in my kernel, it might be looking at the queue only and then distributing queue items to the slave entities in my kernel, which are going to process the queue, the normal work that I would associate with each queue item. And then the other end of that queue is my host code feeding work, or perhaps even another GPU, right? There's any number of possibilities here. However, that sort of a kernel design, which is waiting for work and then processing the work when data becomes available, might be something that I would want to design using a so-called persistent kernel. And a persistent kernel has this kind of distinction. Instead of doing a fixed piece of work, like working on one queue item and then returning or exiting, it sits there and waits in a loop and waits for additional work. It doesn't always have to imply a wait, but a persistent kernel has this idea of operating for a long period of time. And so very often in a persistent kernel, I might have multiple different phases of activity going on. And as a result of having multiple different phases of activity, there may be a need for synchronization. And since I'm operating in the confines of a single kernel, using the kernel launch boundary for synchronization isn't really attractive anymore. And so now I really need something called a grid-wide sync. And so this is a motivator here when we talk about master-slave, producer-consumer, persistent kernels. The idea of a grid-wide sync becomes a very attractive capability. Why else might I want a persistent kernel? Well, one of the things that we talk about with kernels is their state. And state is just data, basically. But state can live in different places. And some of the state that a kernel may have associated with it is data that lives in registers or shared memory. Both of these types of storage mechanisms in our memory hierarchy are ephemeral. What I mean by that is when the kernel ends, those things disappear. The next kernel doesn't get to access the state of shared memory that was left behind by the previous kernel. They're logically separate. There's no logical connection. And they might even be physically changed. So that's not a valid construct, is to declare shared memory and then assume that it's populated with something. It's not, logically. The same is true for registers. Registers are not a CUDA API or a CUDA programmer aware idea, but nevertheless there is data in registers in the GPU. And through intelligent design, I might want to be able to take that data and have it persist. And so I might be interested in using a persistent kernel for the idea that I have a large quantity of state, in other words, data, that's resident in shared memory or registers, which are both ephemeral, and therefore I would rather not have to terminate my kernel in order to transition from one phase of activity to another phase of activity, because I need that state in both phases. The alternative would be to just laboriously store all of that out to global memory and then allow my kernel to end and then launch a new kernel to handle the next phase of activity. That would be the typical kernel launch boundary prior to cooperative groups. And I would have to laboriously save all my state and then reload the state into shared memory or registers, as the case may be, and then begin processing in my new kernel. And that, for some kinds of kernel designs, some kinds of activities, could be a very significant limiter to performance, to have to shovel all that data out to global memory and then pull it in every time you switch phases of activity. So there's lots of good reasons why the grid sync enables some of these interesting kernel design paradigms. Yes, you could say that what I've been, so the question is something like OpenMP task level parallelism. Yes, you could say that when I start to talk about, normally when in a CUDA programming model, in all the ways that we've been thinking about CUDA so far, I would normally tend to think about things in a data parallel way. I want every thread to be doing approximately the same thing, and I just want the data to be different. And the GPU, truly, that is the sweet spot of the GPU. But not everything is immediately amenable to that. And so if I revert or use something like a master-slave approach, producer-consumer, or just specialization, right? Specialization doesn't have to be limited to two entities, A and B. It could be every thread block in my grid could be doing something different, conceivably. And when we start to think about kernel designs that way, we may want to think about those as being akin to task-level parallelism instead of data parallelism. There's data parallelism within the thread block, presumably, but across thread blocks, if I have specialization of behavior, I would now probably refer to that as being more like task parallelism than I would data parallelism. Okay, let's now talk about the multi-grid group, and I'm not going to spend much time here, very little time at all, actually, because I think this conceptually is quite similar to the grid group. However, we're just extending this to multiple devices. Now, it's multiple devices in the same machine, not distributed across separate machines. But if I have multiple GPUs in the same machine, and if I test an appropriate capability indicator, as I'll talk about in the next slide, then what I can do is write a kernel and launch that kernel on multiple devices in this machine. And those kernels can hit a sync barrier, just as we're depicting in the device code here. And now the synchronization will be not just at the thread block level, and not even just at the device level, but that synchronization barrier will be logically the same across the code that's running in different GPUs. And therefore, GPU A, all of the threads in its grid, will hit this barrier and wait until GPU B, all of its threads have hit this barrier as well. And then both GPU A and GPU B threads will be released to proceed beyond the barrier. So this is a really kind of an amazing capability that is part of cooperative groups. And of course, as I mentioned, there is a property that you should, good practice is you don't just assume you have this capability. The good practice is to query the cooperative multi-device launch property, and if it's true, then you know that you are in a machine that's capable or has this capability. Likewise, when I launch a multi-grid group or a multi-device group, there's a new launch API, and it's different than the single kernel or the single device cooperative groups or cooperative grid launch API. So there's yet another CUDA launch function that's designed to launch the multi-device stuff, and the API name is depicted at the top of this slide. One of the things that I mentioned previously is I didn't want to go through the details. What I'll do here is summarize the details by saying what we're going to do is acknowledge that each device needs a set of parameters. Those parameters basically have to carry all of the information that we could think about that was encoded in the triple chevron launch syntax. So of course we need all the kernel arguments, but we also need the up to four parameters that are encoded in the triple chevron syntax or the kernel launch configuration syntax. Those are the grid size, the block size, the amount of dynamic shared memory, and the stream parameter, okay? And so we see that all of these things are captured now in a set of parameters which belongs to a struct, and we're going to pass the array or a pointer to the array of structs corresponding to the number of devices that I have. We're going to pass the pointer to the array of structs to my multi-device launch function, okay? And so each device is going to have a struct. Each struct is going to have all of the things that you would think of associated with the kernel launch that I just went through. And by having one struct per device, I can launch all of the devices that way. The previous one that we looked at, the single device one, effectively is carrying with it all of the data associated with a single struct. Now, because it's a single device, we don't pass it as a struct. We actually just have a list of parameters. But if you understand the concepts here, you'll easily latch on to how to launch a single device kernel launch as well. Okay, let's transition now to our last topic, which is coalesced group. The idea behind a coalesced group is getting back to ideas associated with the warp and warp execution behavior. And we learned what a warp was in Module 3, I believe it was. A warp is something that's associated with the low-level execution behavior of the GPU. We talked about the idea that a warp is a set of threads executing in lockstep. In other words, when an instruction is issued to one thread in the warp, it's issued to all threads in the warp. And we learned also that the warp size was 32. It doesn't have to be. The CUDA programming model tries hard to avoid defining the warp size as 32, but nevertheless, it's been 32 for every GPU we've ever built. And so CUDA programmers have sort of become accustomed to that size. So we'll just generically talk about a warp as being of size 32 threads. Won't always necessarily be that way in the future, but today, and for all of previous history, it has been of size 32. So once we understand the concept of a warp, we may ask what happens in the presence of conditional code where there would be a split in the conditional behavior between threads within a single warp. Well, what happens is you get something called a diverged warp, and there's an execution engine which handles this so-called diverged state or divergence, warp divergence, and it allows some threads to follow the if path and some threads to follow, or the then path, and some threads to follow the else path without going into a lot of the details. Nevertheless, there's an executional engine that allows for diverged behavior. And so if we think of some threads following one conditional path of execution and some threads following another conditional path of execution, then we can quickly realize that there are situations when we won't have a full warp, or we might not have a full warp at our disposal at this given point in my code. Nevertheless, I might want to be able to organize flexible group behavior at that point in the code. I might want to be able to effectively say, for whichever threads happen to be executing with me right now, let's do this. Okay, that's the idea behind coalesced groups, is tell me which threads are currently available to me, currently in my converged group, that are currently with me executing in lockstep, and let's get all of us together to do some work collectively, cooperatively. Okay? That's the idea behind a coalesced group. So we're going to start out by asking that question. We're going to say, tell me which threads are currently executing together, currently executing in lockstep, currently converged. And it's going to be some pattern, if we drill into the execution, it's going to be some pattern of threads within a warp. So if we thought about 32 threads within a warp, there's some group of those threads, not necessarily all adjacent, but there's some group of those threads that collectively are executing at lockstep on this instruction. It might not be all 32. So the first thing I'll do is define this thing called a coalesced group. I'll give it a name called active. and I'm going to use a maker function which returns an opaque entity into the active object that gives me a handle to use to refer to this group that is currently executing in lockstep. Okay, that's my first step, create the group. Now, what's going on under the hood? Okay, let's talk about now what could happen. So I started out with a coalesced group called active, and that the size of that group might have been 8 threads. In other words, there was some previous conditional behavior that caused my warp of 32 threads to subdivide, and right now I'm with a group of 8 threads that are all executing together. Okay, and that all of that idea was encoded or captured in this object called active. Okay, now at that point I may have additional conditional behavior that further subdivides my group or further subdivides my behavior, right? So I might now hit an if statement which only allows some of the threads in this coalesced group to execute the body of the if statement. Okay, and let's pretend that that if statement resolved in such a way that only 3 of my 8 threads proceeded to the body of the if statement. Okay, at that point I can define another coalesced group in exactly the same way, which says tell me which threads I have now. Okay, and in this case the size of the group is 3 because of the characteristics of this if statement, whatever it is. Now underneath the hood, don't get confused because this is an opaque object and you don't really readily get to see this information based on the active object or the G1 group. But underneath the hood, we might have this group of 3 threads consisting of warp lanes of 1, 3, and 7. It could be, right? It's possible. If I were to write code that had to flexibly operate regardless of what my warp lane number was, I'm going to end up writing a lot of code to do some indexing, for example. Okay? And so this creates a situation which is sort of unpleasant if I want to be able to handle this flexibly, writing generic algorithms that work flexibly. Okay? And so this idea of trying to use the internal warp lanes or lane mask would be very inconvenient. And so what the purpose of creating this new coalesced group called G1 is that I can now do things like take the thread rank, and I now get a nice orderly sequence of 0, 1, and 2 across my group of 3 threads. Okay? So this makes it much easier to write parallel algorithms. They're going to pop up and work with whichever threads happen to be available at this point. Okay? Because I have a way of ordering those threads in a nice consecutive fashion, a unique thread rank. Okay? And when I do an operation on this group, like a shuffle operation, which is available for a coalesced group, when I do a shuffle operation on this group or any other available operation, it will work just as you'd expect it would work for a group of 3 threads numbered 0, 1, and 2, even though under the hood, the actual warp lanes that are participating are 1, 3, and 7. Okay, so there's an automatic translation of this idea from thread rank to warp lane under the hood. If I wanted to, I could subdivide this group using the methodologies that we've learned about already. I could take this group and create some tiled partitions out of it, and I still have the requirement that the size of these tiled partitions have to be a power of 2 less than 32. But I can do even weird stuff, like I have a group of 3 threads and I can create tiled partitions that are of size 2 out of it, which means that I'm going to, in this particular case, I'm going to have 1 tile which has 2 threads in it and 1 tile which has 1 thread in it. And you, as a CUDA programmer, need to take that into account. So, for example, you should use things like the dot size construct when you're organizing your thread activity, just like we did in our previous example using reduce. Okay? Should not assume that this sort of a tiled partition is always going to have 2 threads when I am deriving it from a coalesced group. And at the end, let's say, of this if statement, I can force reconvergence of the original 8 threads using a sync barrier. Okay? And again, this isn't going to necessarily apply warp wide or at some other width. It's going to apply only to the width of the groups that are named, the threads that are named in my active group. Now, does that mean I'll only have 8 threads that are converge at this point? Not necessarily, but I will have those 8 threads that belong to that active group converged at this point. There could be more, but there will be, at a minimum, those 8 threads. So why or how might I use this? And this, I think, will probably be approximately our last slide. The example that I'm going to throw out there is something called atomic aggregation. So we learned about atomics in Module 5, I believe it was. And atomics have a lot of useful characteristics, and we can even do things like reductions with atomics and many other things, like reserving space in a queue and things that we learned about in Module 5. Let's suppose I have an operation that's being handled grid-wide, and potentially every thread in the grid is going to do an atomic. Like, let's take a very simple example. I'm going through a big data set, and I'm searching for a match, a matching hash, or just a match. And when I find a match, I might want to increment a variable that says I found a match. And maybe even I want to do something like reserve space in a queue using that incremented variable so that I can record the location of the match or the type of match or whatever. Atomics are great for that. They're great for keeping track of a single incremented variable grid-wide, and they're great for reserving space in a queue grid-wide. However, we know from Module 5 that the performance of atomics is not necessarily the same as the performance of ordinary access to global memory. And so what I would like to do is use atomics sparingly. They're certainly valuable and nice to use, but I would like to, as much as possible, limit my use of it. So what we're going to do is observe that if I have a group of threads that are executing together, previously we might have talked about threads in a warp, but let's remove ourselves from that notion and now talk about a coalesced group. If I have a set of threads that are executing together, then maybe what I could do is have those threads communicate with each other so that we know what level of atomic activity needs to happen, and then just have a single thread do the atomic. Wouldn't that be cool? It could result in a significant reduction in atomic pressure when considered across a thread block or across a grid. Okay? If I have a lot of atomic activity going on, atomic aggregation at the group level could result in a significant reduction in atomic pressure. So let's walk through this code and see how that is accomplished. So I'm going to use this atomic ag inc just like I might use atomic increment or atomic add maybe. Really, this is an atomic inc function because the assumption here is that I'm incrementing by 1. If I hit the atomic, the objective is to increment by 1. And so that's really more like an atomic inc function, but it would be straightforward to extend this to atomic add as well. We're going to start by saying which threads are executing together. Which threads can I use to cooperate for this reduction of atomic pressure activity that I would like to undertake? And so the first thing I'm going to do is declare a coalesced group G that are the set of threads that are currently executing in lockstep at this point. Now, as we start to unpack this code, let's remember that the way that we're using this is not unlike the way that we would use the atomic inc function. And so presumably, let's say we're doing this searching and matching across the grid that I described. Presumably, I've got an if statement that says if I found a match, if my thread found a match, then I want to increment the global variable. That means that by the time that I hit this atomic ag inc function, I already have a reduced set of threads. Probably, right? It might be all 32 threads in a warp, but it might be some lesser quantity of threads, okay? But furthermore, I also know implicitly that all those threads want to do the atomic inc, okay? Because I called this function. I'm going to do the atomic inc. I'm using this just like atomic inc. If I called this function, it means that thread wants to increment the variable, okay? So first I do is gather together the group of threads that are executing together. And then I'm going to say, I really only want one thread to perform the atomic. And instead of incrementing the variable by 1, I'm going to increment it by the number of threads that are actually executing together. In other words, it's the number of threads that want to do the atomic inc at this point in time. And so what I'm going to do is declare a master thread. And I'm going to say, if my thread rank is 0, that's the master thread. And the master thread will be responsible for doing the atomic operation. And because it's now not just incrementing by 1, but incrementing by the number of threads that are executing together, I'm going to use atomic add, not atomic inc. But I'm going to use the pointer to the location to be incremented. And this amount of addition that I'm going to do to that location is equal to the size of my coalesced group. Because as we stated already, the number of threads that are currently executing this statement, this coalesced group, this atomic ag inc, is the number of threads that want to increment that variable. Therefore, the total increment to that variable is going to be equal to the total number of threads in my group. So I can just use g.size for that. That takes care of the atomic operation. There's only one thing left we have to do. An atomic operation returns a value. If I do an atomic inc and I get back a value of 3, it means that when I read that variable, it was 3, and I incremented it to 4. And so 3 is the value that was in the old value that was in that variable that I just incremented. So if I'm going to do atomic inc across a group of threads, then I would expect that one of those threads might get 3, one might get 4, one might get 5, one might get 6, one might get 7, let's say, if they all happen to hit the location at the same time. Each one is incrementing, and in each one in sequence is reading the incremented value from the previous one as its old value. So I can't just return the same previous value, because if my value started out at 3 and I incremented it to 8 or added a value to it to make it 8, I can't return 8 to all the threads. That wouldn't be functionally correct. What I have to do is return 3 to one thread, 4 to another thread, 5 to another thread, 6 to another thread, 7 to another thread. And so the final line of code does exactly that. Okay, we're doing a shuffle operation across the threads in the group to distribute from thread 0, the master thread, the previous value. In other words, the value is returned. That previous value would be 3 in this example if I went from 3 to 8. Okay, it would be 3. So I'm returning that value, the previous value, plus the thread rank, which is 0, 1, 2, 3, 4, 5. That's going to give me a nicely distributed value across the threads in my group. Okay, so that's how that would work, and that is a very interesting and clever way to use atomic aggregation, or to create atomic aggregation using a coalesced group. Last question in the chat. Does the group sync at the end of the function implicitly? No. Quite simply, no. Does not. Now there's a question, what about atomic blank 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 underscore system for cooperative groups? So the idea behind atomic underscore system is that it is communicating or is enforcing an atomic behavior, an atomic read, modify, write behavior amongst multiple processors. Really doesn't have anything to do with cooperative groups. It also requires a certain kind of capability between the processors. You can read more about it in the programming guide, but it is a mechanism, for example, that would allow me to do an atomic update to a single variable from both the GPU and the CPU. Okay? So they both could be doing atomics to a single variable, and that variable should behave correctly if I do atomic blank 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 underscore system, and my architectural capability supports that capability. That concept, I would say, is mostly orthogonal to cooperative groups. Not to say that you can't use it. Orthogonal means they're independent. One does not conflict with the other. Okay. Yes. So the next question is, so here there is no race between writing previous in thread 0. Remember, previous is a thread local variable, so I'm not sure how a race condition would occur. Normally a race condition requires 2 or more threads to be active in order to have a race condition. Prev, P-R-E-V, the return value, is a thread local variable. Okay? There's only one thread that has access to PREV. Thread 0 has its own PREV. Thread 1 has its own PREV. Thread 2 has its own PREV. And the only way those things get communicated to other threads is through the shuffle operation. Okay? So here there is no race between writing prev in thread 0. No, there isn't. Thread is written in prev 0 as a result of the atomic add. And then writing it in the other threads because the threads are coalesced and so they work in lockstep. Yes, the threads are coalesced and they work in lockstep, that's true, but there couldn't ever be a race condition on prev because prev is thread local. Each thread has its own local copy of prev, which only that thread can access. Okay, so that brings us to the end of our material, and this is all good material that you may be interested in. If you'd like to hear some other people who are actually way smarter than me talk about many of the same ideas that we presented here, I would direct you at the first two presentations listed here. If you'd like to look at sample codes, pretty much any sample code that has a capital CG in it means that it has either is focused on cooperative groups or has been reworked, let's say, or has been designed to incorporate cooperative groups as part of some other functionality that's focused on, right? So obviously conjugate gradient multi-block CG, one of the key items of exposition there would be the idea of the conjugate gradient methodology, but also it's going to use a CG or cooperative groups methodology. There's some blog articles on cooperative groups. There's a programming guide section. I would encourage you to refer to this especially if you're going to use grid group or multi-grid group, because there's some nice little snippets in there that are easy to copy and paste and drop in your code. And then the last item in this further study thing is really sort of off topic. It doesn't have anything to do with cooperative groups directly, but it's an interesting article that talks about the desire and the need for this ability to retain persistent state. So if you're interested in persistent kernel design and some of the motivations for that, you can see some of the motivations in that article that's at that GitHub link. There is a homework available, and I'm going to turn it over to Robbie in just a minute to walk through the homework, and that will bring us to the end of our slides. So, but what prevents the shuffle from bringing a previous before the atomic add wrote it in thread 0? Okay, let's go back to that. What prevents the shuffle? So the shuffle is prev. Okay, I see what you're getting at now. And it looks like maybe you would want to have I agree that you might want to have a sync, a g.sync operation after the if statement. In other words, you want all of the threads to wait until the atomic is done before you allow the shuffle operation to proceed. I think that is correct. So you could say, I think you might say that this slide has a bug in it. I hesitate to pass judgment immediately, but I think that's a good observation. You might want to add a line to this slide like this.
Maybe not. Maybe the shuffle will synchronize it in some sense, because thread 0 has to do this. There's no else to the if.
Yeah, that's a good point, actually. So I think that's it. So one of the things that we learned with the shuffle operation, I'm not talking about cooperative groups now, but if we go back to shuffle, we learned that shuffle went through a transition in the CUDA 9 timeframe, where the original shuffle operations were deprecated, and then we had a shuffle sync operation. That's exactly right. So that's another good observation. So that's why there's no bug in this slide. So the idea is, with a shuffle sync operation, now I'm talking about a shuffle that has nothing to do with cooperative groups. I'm talking about the intrinsic. With a shuffle sync operation, we must pass a mask parameter, and the mask parameter specifies to the shuffle operation the threads in the warp that must participate for correctness. That's exactly right. That's why this gsync is not needed. That's talking about the mask parameter passed to a shuffle sync operation in a non-cooperative groups realization, but post CUDA 9. This g.shuffle operation is implicitly passing a mask parameter that corresponds to the thread pattern associated with the threads in the coalesced group called G. What that says then, syntactically, is before you complete this shuffle operation, you must, if they're not reconverged, you must reconverge the threads in this group. And that's why this is correct as written. Very good. So, good job. So there's, the shuffle won't get done until thread 0 execs it 2. Yeah, so the shuffle won't get done, I would say, because of the synchronization, the resynchronization requirement that's implicit in the cooperative groups variant of the shuffle operation, which is under the hood passing a mask parameter that is matching the thread pattern associated with the coalesced group G. And therefore, that group must reconverge before that shuffle will complete. And the only way that group could reconverge at that point is if thread 0 has completed its atomic add. Okay, I don't see any more questions in the chat, and I'm keen to get onto the homework because we only have about 20 minutes left. So I would like to, if it's okay with everyone, I would like to turn it over to Robbie at this point. So I'm going to stop sharing. And Robbie, if you're available, if you could do whatever you think is a quick walkthrough of what you wanted to present over the next 10 or 20 minutes, that would be great.
Sure. Thanks, Bob. All right, let me share my...
So before Robbie's sharing, this is Helen, and let me just insert some words here in case some people drop off earlier. Just Helen here from NERSC, just wanted to represent Kevin, God, and myself to show NERSC side appreciation for this long series that for the CUDA training. I want to thank Bob for the always in-depth presentations, and thank Robbie and Max help with exercises and helping users. I want to thank Tom for organizing the overall events and to for inviting NERSC to join this series and benefits our users. I want to thank our users to stick to the end. Thank you all, and I'm sure you all learned a lot. And just want a final reminder for the attendees, please do your surveys to help us. And this is the last piece of survey. Feel free to add not only your comments for this one, but also for the overall series. We appreciate it. Thank you all. Now, Robbie, please.
Thanks, Helen. Okay, so I'll just do a really quick run through of the homework for today. The homework is split into 2 exercises, and basically, let me share my terminal real quick, actually. There we go. Basically, the first exercise is going to focus on how do we actually create groups and partition groups. And then the second exercise is focused on grid-wide synchronization. So if we look at the first exercise on the GitHub page, it asks us to first create, only modify 2 lines and create a group based on our thread block. So if we actually look in the task 1 code, let me open that up. We see a couple things. So we see a kernel launch at the bottom in our main function, where we launch a kernel with 1 thread block with number of n TPB is number of threads per block, which up top is set to 256. So the first thing we're going to do is we're going to create a group from that thread block. It's going to be a single group. So in this auto G1 line, we see a fix me statement in here. And we're going to replace that with this thread block. Bob kind of went over these API calls in the slides, so this is just to give you an introduction on, as to how they're actually used. And then down here, this auto G, notice the comment says, for each task, adjust the group to point to the last group created above. So we just created group 1, so we'll just point it to group 1. And when we run this, if I refer back to the instructions, I should get a group partial sum of 256. So basically what this exercise does is for each group that we create within our thread block, we're going to get a partial sum that just tells us basically how many threads are in that particular group's partition. So if I go ahead and compile this, we are using the C++ 11 standard, because if you noticed in that source code, there is an auto type to tell the compiler to automatically deduce the templated type. If I run this, I should get a single line of group partial sum of 256. So that is working correctly. Now, the second subtask in task 1 asks us to partition this group. We want to subdivide this into a set of 32 thread partitions using the dynamic runtime partitioning method. So basically, so we know we have a thread block that contains 256 threads. So when we partition this into 32 thread partitions, we should now see 8 lines printed out, 1 for every partition. And they should each say that they have 32 threads in them. So I'm going to go ahead and use the tiled partition API call here to set up our second group, which is auto G2. And I'm going to partition the first group that we created into 32 thread partitions. And then I'm just going to set this group pointer here to the last group that I created, which is G2. I'm going to recompile and rerun, and I should now see 8 lines, each saying that they have 32 threads in them. The instructions then say to create a third group, and just instead of decomposing this particular group into partitions of 32 threads, it asks you to partition it into 16 threads. So we should get twice the number of partitions, each saying that they have 16 threads. So if I go back into task 1, I can do the same thing here for group 3, where I used tiled partition. I'll take group 2, partition it into partitions of 16 threads, and update my pointer and now I should see, 16 partitions of 16 threads. That pretty much concludes exercise 1. So that's just showing you how you can create a group and how you can use dynamic partitioning for the groups that you create. And then exercise 2 is focused on grid-wide syncs. So Bob kind of mentioned this earlier, where you can kind of have an implicit synchronization by using multiple kernel launches, but that might not always be sufficient. So he showed us the API calls earlier to implement grid-wide syncs, and task 2 is set up to allow us to kind of play around with that. So the first thing we have to do is inside of this myRemoveIf function, there are some fixed mean lines in here where we're going to insert some synchronization. So we're going to insert thread block synchronizations within thread blocks, and then one grid-wide synchronization at the end. So if you see, we have a group here that's this thread block, auto G, and then auto GG is set to this grid. So if we want to do a thread block synchronization, we can just go into this line and do g.sync. And in fact, all of the, this other one is also going to be a thread block synchronization. Excuse me, all three of these actually. And then we're going to use a grid wide barrier outside of this grid stride loop. So we're doing thread block synchronizations inside of the grid stride loop, and then outside of the grid stride loop, we're going to do a grid wide barrier. So here we would just do gg.sync. So we would just tell it to use the group that corresponds to the grid instead of the group that corresponds to the block. Let's see, what else do our instructions say? They say in the host code, modify the fix me statements to do a proper cooperative launch. So Bob mentioned you can't use the triple chevron syntax anymore to launch a kernel this way. If we did that, all the synchronizations that we just inserted would be silently ignored, and that's not what we want. So if we move down to our main function here, let me put that into focus. Let's see, we have two cooperative launches. We have one here, and we have one down below too, if I remember correctly. Or is it up above? Why am I not seeing it? I'll find it in a sec. So anyway, the cooperative launch device function call takes a couple of different arguments. So it takes a void pointer to a function, so to our actual kernel. That's already there in that line. It takes our grid dimension, our block dimension, which are both dim3 objects, so they can be single dimensional or they can be multidimensional. It takes a list of arguments. It takes a shared memory size and a CUDA stream. So we have to insert all this stuff into our kernel launch here. So we have the grid and the block dim3 objects created right here. So I'm just going to simply pass those in. Say grid, block. Args is also right above. You see the void pointer up here that has a list of the arguments to our actual kernel. Well, I'm not going to use shared memory for this. And we already created a CUDA stream str right up here. So I'm just passing that in simply. And then there should be another launch right here. Yeah, here it is. I don't know why I wasn't seeing it before. All right. And now in our instructions, have our compiler flags. And I have a syntax error. And if we run this, this has an error checker built in, so it will give you a mismatch message if there is a mismatch in the results, but we shouldn't get that. We should just get our correct output according to our instructions. Say we should get a description of the number of SMs, the number of blocks per SM, the kernel time, and the thrust time. And in fact, that's what we get. So the instructions also note the above informational data contains occupancy information. Note that we're able to put 8 of these 256 thread blocks onto a single SM for a full maximum theoretical 2048 thread complement per SM. This is 100% occupancy. The kernel is fairly simple, so there's low resource utilization. And then there's an optional component at the end that says that you can compare the operation to an equivalent operation in thrust. And for a trivially small data set size, our monolithic kernel seems to be faster than Thrust. Run this small data set size using the Nsight Compute Profiler to confirm for yourself that Thrust is actually doing 2 kernel calls to solve this problem, and then make the data set larger and see if that changes, which is faster, Thrust or our naive code. And that's pretty much it. These API calls are fairly simple to use once you understand conceptually what's going on the back end. Does anyone have any questions here? I wasn't looking at chat. The William mentioned in here the C++11 standard is important, otherwise the compiler will throw errors. Yes, because we're not explicitly declaring types. There's that auto type in there. So that's why you have to include that flag. Is there any other questions?
All right, if there's no other questions, then I would like to just thank Bob, Robbie, and Max for another great module in this series, as well as thanking them once again for helping to put this series on as a whole for OLCF, for NERSC, and for anyone else who ends up participating in this. Whether it was during these events or afterward, if you come back and check out the any of the recordings or whatnot. So thank you all again for putting this together. Thank all of the participants for joining us. I know there's a handful of folks who are here through all of it. And so we hope that you gained a lot of knowledge out of this, or can go back and maybe pick some extra things up afterwards. So thank you all again very much. We appreciate your participation.